Okay. This is not your final lecture for chapter 24, but this is the final lecture you need before you start the homework set that's due on Wednesday. So hopefully you watch the first video before class on Monday, and we'll kind of talk through some of those concepts and about equipotential surfaces. And in that first lecture, I gave you the definition for electric potential, so that's our first useful equation. So it is just a definition. And then just we reminded ourselves of the relationships between work and energies. So that work is equal to the change in kinetic energy, which is always true. And in the case where we have no friction, which is, for us, all these problems in this chapter, we're assuming that. So the change in kinetic and change in potential would be equal but opposite. And then in the second video, we worked through a problem that really just deals with these two equations, but gave us this third relationship. So relating the electric potential, change in electric potential for a particle to the electric field. And so the last thing that we're going to come up with, which will be a fourth separate equation, is the electric potential from a point charge. So I mentioned in the first lecture that this electric potential, and then something that we're going to continue to talk about next week, capacitance. These are things that take us from the world of electrostatics, where charge is not moving, into the world of current, where charge is moving and useful, and we can picture it much more tangibly. So we're still kind of in that murky world of linking electrostatics to moving charges. And so as we do that, we're actually going to look still at the point charge system. So systems where we just have a couple of charges, not a huge number of them. And so what we want to do is find the electric potential from a point charge. So there's a little bit of a derivation. I'm going to talk through it conceptually a little bit. It'll feel like I'm waving my hands at it a bit. In the textbook, if you're reading the textbook along with me, they do it in more calculus notation. Just because of the situation of me being here and you watching me on videos, I've fallen away from that calculus notation and into more the algebra based, since I know all 13 of you are good with algebra. But it's the same process either way, it just slightly changes the notation. So if I have a point charge, so here's my point charge and it is Q. And I want to know what's the electric potential at some point r away from this point charge. We say, okay, well, what we're going to try to find is an equation. Electric potential is equal to what? So I'm going to actually start with that third equation. Change in electric potential is equal to negative E times D, where E is the electric field that is generally given, and D is the distance we are away from the source of that electric field, or the displacement that something moves. So for this particular problem, we're going to say delta V is equal to and again, this is not how to solve a problem, just deriving something. Negative E. E for a point particle is 1 over 4 pi epsilon naught times Q over R squared. You could call this K as well. 1 over 4 pi epsilon naught and K are the same thing, remember? And if I'm the distance D, well, I call that distance R on my picture, and we often do. So what we see is one of the R's cancels, right? So my change in electric potential is equal to negative 1 over 4 pi epsilon naught times Q over R. Now, this change in electric potential is not the same as saying, what's my electric potential right here? So the change is equal to the final minus the initial, right? And I'm saying that is equal to negative 1 over 4 pi epsilon naught Q over R. So this is where, just bear with me, because this is a derivation, and I'm not describing the whole thing because I'm watching the clock of how long this thing will take to upload. This is my initial point. If I have I'm looking for the potential here. If I have something, like let's say I put a positive charge here and it has some potential here, what will happen to it when I let go? The positive charge will be repelled and it will move away out to where it has no more potential. It will stop moving. So as it turns out, its final potential is 0. Wherever it ends up, it has lost all of its potential, right? If it's a negative charge, it'll actually be the same. It just comes zooming into here. Ooh, sorry, I don't know what's going on upstairs. But wherever it ends up, it will have lost all of its potential. So the final electric potential is 0. The initial, when I'm at this place where I'm asking about it, then, well, I have a negative and a negative, right? They both go away, or I can cancel them. So the potential at that point is 1 over 4 pi epsilon naught times q over r. And that, now that we know it, is an equation. We're just going to either follow it along there and it makes sense, or you're going to believe me. But this is the electric potential from a point charge. So you can only use this equation for point charges, meaning like 1 or 2 or 3 charges. These other 3 are true for all scenarios. So whether I have continuous charge distributions, very complex things, simple things, whatever, these 3 things are always true. This final equation is true for point charges only. Now the nice thing is, as I mentioned, electric potential is a scalar. We do not have to worry about vectors at all, which makes these problems so much easier to deal with than everything we have been doing prior to now with electrostatics. So I'm going to go through 2 practice problems with you. The first one is kind of looking at how these things are so much easier, even though they can have some geometry. So on your PowerPoint, there's a picture. So I had 2 charges. I had a negative charge called Q1, and it was equal to negative 50 microcoulombs. And then I had a positive charge over here called Q2, and it was equal to positive 50 microcoulombs. And then I had an axis running like so. This was like 0.26 meters. This was also 0.26 meters. And I asked you to find the electric field at 2 places, A and B. Let's just do A. So A was up here, and this was 0.3 meters. And I think even you have this. There's like a lot going on in this picture. Oh my lord. This was 0.6 meters. Okay. So it's like, you know, if you look at that, and so I'm saying, find the electric potential at point A. So for electric force or electric field, dealing with something at A would be a hassle because this is a triangle, and so you'd have to be dealing like X components and Y components and figure out angles and yada yada. You just did it on the electrostatics test you turned in last Friday. So it's a little bit of a pain. Electric potential, super easy because it's a scalar quantity. I don't care about the geometry of the system. So when you're finding electric potentials from point charges, there's 2 important things to remember. Number 1, when you use this equation, you need to put the correct charge in, like put a positive sign if it's positive, put a negative sign if it's negative. This is something I mentioned in the last video. The other thing is if you have multiple potentials. So here I'm going to have a potential from charge Q1 and I'm going to have a potential from charge Q2. To get your total potential, you just add them. Again, it's not a vector, you just literally add them. So if I were going to solve this problem, I would say V1 at point A is equal to 1 over 4 pi epsilon naught times Q, which is negative 50 times 10 to the negative 6 coulombs, divided by R, which is 0.6 meters. And so if I plug that into my calculator, I get negative 750,000, so negative 7.5 times 10 to the 5th volts. So it is plug and chug. Just be careful, the sign of the charge will give you the sign of your V. And then if I want to find the voltage from charge 2, it's 1 over 4 pi epsilon naught. Again, if you're putting K's here, that's fine. The AP test is going to use this notation, so I'm trying to slip into that. Times the charge, which is 50 times 10 to the negative 6, it's positive, right? Times the distance from Q2, which is 0.3 meters. So that's the only place the geometry matters, is just like how far away are you, and that's it. And so when I plug this in, I get positive 1.5 times 10 to the 6th volts. So my total voltage is just V1 plus V2. Again, they're scalars. I don't have to add them up as vectors. I just literally add them. And so my total voltage will be positive 7.5 times 10 to the 5th volts, and that's it. So when you have systems of point charges, and some of the homework problems do this, you just plug and shove, find each voltage from each individual point charge and add them to get your total. Just be careful to put the correct sign in for your Q, and you should be set to go. One other type of problem that's maybe not as intuitive is finding work done with moving things in point charges. So here's just like a stationary point. I have a point A, just some random place, and I want to know what's the voltage from these other charges at that point. But what if I'm moving charges around? That can change things a little bit. So I'm going to work through one of those. Okay, so that kind of links up these equations a little bit. So I have a charge, a positive charge, which is 20 microcoulombs. And I have this, again, seems a little bit abstract, but I have another positive charge, it's smaller, it's 3 microcoulombs. And I'm going to move it from a distance of infinity. Remember that I made my infinities weird. I don't like my infinities. I'm moving it from a distance of infinity away, so it's very far away, to a distance 0.5 meters away from this other 20 microcoulomb charge. Because they're both positive, remember, if I let it go, it's going to just zoom out to what we say infinity, to where it has no voltage. So it takes some work to move it in closer to this charge. And so the question is, what is the work done to move it? Let me find the work done on the little charge, so the plus 3 microcoulomb charge, to move it from a distance of infinity away to 0.5 meters away from this other charge. Okay, so I'm going to find work done. So if I think about, well, okay, what do I know about work? Work is equal to the change in kinetic energy or the negative change in potential. I'm going to go with negative change in potential. So it's equal to the negative change in potential energy, which is equal to, potential energy is Q times V, right? Just based on this definition of what potential energy is. So we can say work is equal to negative Q times delta V, which would be negative Q times the final velocity, or not velocity, sorry, I have honors physics in my head. We're doing energy there, but it's with actual motion. Final voltage minus the initial voltage. Okay, so how do I find the voltage? Well, this is voltage from a point charge. It's from this point charge, right? So this is the thing moving. This is the thing creating an electric potential. So we say work is equal to negative Q times 1 over 4 pi epsilon naught times, and so you have to think, well, which Q? It doesn't really matter because it factors out, but Q over R final minus 1 over 4 pi epsilon naught Q over R initial. Okay, so what I'm saying here is this little Q, again, it doesn't matter because I'm going to factor out and it'll be Q times Q. You can't mess it up. But the little Q is the thing that I'm doing the work on. It's this thing. And in the electric potential, that's the thing producing the potential. This is the thing like repelling this, producing some electric potential between those two. Think of this as like, this is like my charged wall, right? And this is the particle moving around. Okay, so I can, looking at this, I can factor out a lot. So this becomes work is equal to negative Q over 4 pi epsilon naught times Q. So the two charges are multiplied together, times 1 over R final minus 1 over R initial. Well, what is R final and R initial? R final is a number, right? It's 0.5 meters. R initial, I'm initially infinity away. 1 over infinity is big fat 0, right? So when I go plug numbers in here, it's equal to negative Q, which is, sorry, I'm trying to see my numbers, 3 times 10 to the negative 6 coulombs times, I'm going to run out of space, times 20 times 10 to the negative 6 coulombs divided by, I'm just going to write 4 pi epsilon naught because that's a constant, you can go look that up, times r, which is 0.5 meters. When I plug all those values in, here's my big equal sign, this ends up being negative 1.08 joules is my work done to move the charge. So when you have, that's just like a weird subset of problems, but when you are trying to calculate work done to move point charges, this is one way to do that. So like so.